So if you recall, in the beginning of this class, I mentioned that statistics involves two major areas. One is descriptive statistics, where you summarize data in tables, graphs and charts, numbers like mean, standard deviation, and so on. And second group was statistical inference, where we start with the population of interest, take sample, and try to figure out like how the population values are. So confidence interval is like that. It is a part of statistical inference. So I showed you this flow chart where you may have a population of interest, and because of various reasons, like we may not have that much funds available to get data on each and every item in the population. We may not have time, we may not have like resources. So what we do, we take a sample. So we use sample to figure out something about the population. So in population, you have population parameters of interest, something like mu, sigma, mean, standard deviation of the population. So we represent population parameters with Greek alphabets usually, like mu, sigma. And when we take a sample and do the calculations, we get sample statistics. And instead of using mu for mean, we use X bar. Instead of using sigma, based on sample, when we calculate standard deviation, we use maybe small s. So those are sample statistics. Our X bar, the X bar, what it is trying to do, we can say X bar is a point estimate of mu. Because we do not know how much is mu, and it is not even possible to get to know mu directly, we try to estimate using X bar. And because X bar is a single point, we call it point estimate. So that is a statistical term, point estimate, because it is a single point. Similarly, you can say S is a point estimate of sigma. So again, since we cannot have access to calculating exact population value for sigma, we do the second best thing. We calculate S based on sample and then use that as a point estimate of sigma. We try to use that and say that probably population will have this kind of variability. Let's talk about an example. So you know, like UMass Dartmouth has maybe more than 8,000 students, and suppose that is the population of interest, and you are doing some project and collecting data where you want to assess how many songs every day a student listens to on Apple Music or Spotify or whatever apps people have, number of songs that students listen to in a day, number of songs per day. So suppose that is our random variable of interest. So it will be very time consuming and also may not be practical to go and ask each and every student at UMass Dartmouth. So there are more than 8,000 students. Some may not be available, some may be sick, maybe in a hospital, someone may have gone to visit family. So it may not be feasible to contact everybody. So what we do is, we do it smartly, we take a sample. Any idea like how many songs people listen to on UMass Dartmouth campus?
Like 30, 35?
Yeah, could be. That's reasonable, right? So I will say, let's say 35 per day. So suppose I ask maybe 30 or 50 students and I get an average of 35 songs per day. But we don't know what would have been that value in the entire population of 8,000 plus students. But we have some idea that it may be 35, it could be more, reality could be more, reality could be less. This number that you see is called point estimate, because it's a single number, it's a single point that you are estimating, so that is called point estimate. But we also know that it is impossible that the reality will be exactly same as this. The chances are almost 0%. So when you actually get data from each and every person, it may be different. If you say 35 plus minus 10, then you are safer. Because if you are trying to hit the actual mu in the population, actual value in the population, with one number the chances are very rare that you will hit exactly that number. But instead of 35, if you say plus minus 10, so you are going like to 25 up to 45, then the chances are very high that somewhere in between your population value will lie. So by giving a confidence interval, actually giving that interval, your confidence rises. This will mean we are talking about 25 to 45 songs. So we are giving a range. Instead of a single value, we are giving a range. So if this number is called point estimate, then this range is called, such a range will be called confidence interval, because it gives you more confidence that the value is likely to be somewhere in between. So that's better than that 35 number, because that's a single number and there's every chance that you may be wrong. In general, what we can write is confidence interval consists of two components. One is called point estimate, because even to get that 25 to 45, you need that point estimate 35, because plus minus 10 is around 35. So you need point estimate, and then you need something after plus minus, which is called margin of error. So your confidence interval includes point estimate as well as margin of error. You may have seen that in presidential races, where if a candidate is expected to get, let's say, 45% of the votes, usually they do not report 45% only. They also indicate 45 plus minus 5% or 7%, because there is always a margin of error. And that margin of error simply exists because we are taking a sample from the population. So if your population is 8,000 students and you are taking a sample of only 30 students, so out of 8,000 you know about 30. So 8,000 minus 30 is 7,970. So you don't know anything about those remaining students. And you are trying to make a judgment based on this 30 and project that to the entire population. So there are a lot of unknowns. If you take a sample of another 30, like new 30, your average may be different from 35. Another 30, average may be just 31 or 30. So there's always some error in our estimate. Whatever we are estimating, there is some error, and that plus minus term is called margin of error. How do we calculate confidence intervals? So in this class, we only look at three situations. Situation number one is, so instead of writing confidence interval, I'm going to write CI, shortcut. So CI means confidence interval for mean, which is population mean, with sigma known, So that is one situation. And then there's a second situation where sigma is not known, and the third is proportions. So if sigma is known, the formula that we use is x bar plus minus z alpha by 2, and then sigma divided by square root of n. So we calculate confidence interval using this formula, where clearly you can see this part is point estimate, and then you have the plus minus term, which is margin of error. The only thing that you may not be aware is this alpha. This symbol is alpha. It is also called a risk level. Like if you have 90% confidence in something, then you have 10% risk. So alpha captures how much risk exists. So if your confidence interval is 90%, then your alpha is 10%. If your confidence interval is 95%, you have 95% confidence, then chances of going wrong is 5%, which is risk. Second situation is confidence interval for mean with sigma unknown. So that is the second situation. First situation that says sigma known is not really that practical, because usually we do not know the values for the population. So sigma is a population value we may not know. What we mean by sigma known is that if that kind of data is getting collected in a business, in a company, like almost on a daily basis for last 4 or 5 years, they have a very good idea about what variability to expect. So in that sense, sigma is known. But second situation is more practical and more useful, because even if, let's say, sigma known, you can assume something, but if you are collecting sample, then why use some other sigma? Use your standard deviation based on the sample. Because anyway you have data, so use that standard deviation. So this one is more practical. So when you have this situation, you calculate x bar, and the margin of error, instead of normal distribution, which is a standard normal distribution z, instead of that we use another distribution called t alpha by 2 and s divided by square root of n. So exactly same kind of format. The only thing is statistical distribution changes to t, and instead of sigma I'm writing s, which is calculated from the sample. And last situation is confidence interval for proportions. Format is same. You start with the average p and then plus minus, and we can still use standard normal distribution z alpha by 2, and then you need square root of p times 1 minus p divided by n. So in this chapter you need just these 3 formulas for calculating confidence interval in any given situation. Suppose average pizza delivery times are normally distributed with unknown population mean and population standard deviation of 6 minutes. So these kind of problems will very clearly tell you that population standard deviation is given, so 6 minutes, sigma known. Random sample of 28 pizza delivery restaurants is taken. So in the first sentence, it also says that those delivery times follow normal distribution. So now we have sample of 28. So somebody may say like 28 is less than 30, because for central limit theorem to apply, your sample size has to be more than 30. But that is for the cases where the original distribution is not normal. But here it says that the original distribution itself, like x, follows normal distribution. Then x bar will definitely follow normal distribution. So sample of 28 restaurants is taken, and they have a sample mean delivery of 36 minutes. Find 90% confidence interval estimate for population mean delivery time. This fits in with the first situation. Situation 1, confidence interval when sigma is known. So let me capture what is given first. So you are given that sigma is 6 minutes, and then you take a sample of 28 restaurants, and you get average of 36 minutes. And the confidence interval in which we are interested, in the problem it says 90% confidence interval. Now confidence interval or confidence level is 1 minus alpha, which is 0.9. 90% we can write as 0.9. The other term that I mentioned earlier is risk level, which is alpha. So if 1 minus alpha is 0.9, then risk is 0.1. If your confidence is 90%, then your risk level is 10%. If you are confident about something at a 90% level, then you may be wrong 10% of the time. So these things are given, and what we are interested in is 90% confidence interval for mu. That is given by x bar plus minus z alpha by 2 sigma over square root of n. So I'm just rewriting that formula. You already have x bar, you already have sigma, you already have n. The only thing we don't know is z alpha by 2. So that's the only thing that we have to figure out. And to figure that out, because this is z, I will draw a distribution for z. As you know, z follows normal distribution with mean 0 and sigma 1. So mean is always 0. If this area is, let's say, 0.9, so we want 90% confidence interval, so that middle portion has to be 0.9, and remaining 10% goes in two tails like 50-50. So that middle portion is 1 minus alpha, this is like 1 minus alpha, so this is alpha by 2, this is alpha by 2. So remaining part in two tails is alpha by 2 each. So if this is 90% and half of 10% is 0.05, and this is also 0.05. This area is 0.05, this area is 0.05, and the middle 0.9, so the total area is 1. This number here is your z alpha by 2. So if we calculate this point on z-axis, so that will give us z alpha by 2, and then we can plug in and get answer. So to get this area, if you recall, we use qnorm. So area to the left of z alpha by 2 is 0.9 plus 0.05, so 0.95. So we want this point where area to the left is 0.95, mean is 0, sigma is 1. So that should give you 1.645. So now you have everything, like all the ingredients are there, now you can calculate very easily. So x bar 36 plus minus sigma 6. If you simplify this, you will get about 1.9. I'm rounding this to like 1 decimal. So point estimate 36, margin of error plus minus 1.9 minutes. So pizza delivery has that much of variability. Or you can even write something like this. 36 minus 1.9 is 34.1, and if you add, you get 37.9. So pizza delivery will take anywhere from 34.1 to 37.9 minutes. And you have 90% confidence. But then you also have 10% risk level, which means there is a 10% chance of you going wrong, which means that your confidence interval does not capture the real population average. What is the interpretation of this confidence interval? So this 90% confidence interval, so what does it mean? So it means if we take 100 different samples, because this is just one sample of 28 restaurants. 28 restaurants, you have taken one sample. If you repeat that same thing like 100 times, so if we take 100 different samples and create 100 different confidence intervals, CIs, because this is just one confidence interval. If you repeat this process 100 times, you will get 100 different confidence intervals. 90 out of 100 will contain population mean, which we don't know. We don't know what is that value. That unknown value will be able to capture 90 out of 100 times. If I have to draw a picture of this, it will look like this. So you have some population mean, which is unknown, and let's say it is this line. At this value is the exact population mean, and you take a sample of 28 restaurants and find delivery times, find an average, and that average, let's say, is somewhere here, slightly above. And then you create a confidence interval going to minus side and then to the plus side. The chances are that it will contain that interval. Now next time you collect a similar sample, maybe 28 different restaurants, and you may get a value which is somewhere here, and you calculate your confidence interval and it captures. Next time you repeat, it is very close, but still is not exactly on the population value, but still with confidence interval you are able to capture. But if you keep on repeating, there may be a chance that just by chance you get all the values, all the pizza deliveries are on the higher side, and even if you calculate a 90% confidence interval, it does not contain the actual value. So that is the risk. There is a risk that it may not. You may not get the reality. If you repeat 100 times, if you are wrong 10 times, then that is called 90% confidence. So your 90% confidence interval does not mean, many times people misinterpret, it does not mean that the interval that you have created, this interval has 90% chance of catching the population value. That's not the interpretation. Interpretation is, if you repeat this process 100 times, 90% of the time you will be right. Same thing with 95%. So your confidence level goes high if you have 95%. Let me open a new file, and then I'm going to save as chapter 8. And close everything else. Clean this. Clean this. History may have a lot of things, so I'm going to clean that. Chapter number 8, confidence intervals. First one that we did is try it. 8.1. So to make these calculations easier, we are going to make use of a library for which you first need to install a package. So let me show you how do you install that package. So you'll go to the fourth window, hit on packages, and then click install. And the one that we are going to use is called BSDA. As you type, it pops up. So I'm going to select that and say install. And once it installs, I have to run this library, BSD. So what is BSDA? Basic Statistics and Data Analysis. So once that runs, I'm going to type the command. So I'm using this function called z.sum. So as you start typing, it will automatically pop up. So select, and then I need to provide what is the mean of x. So mean dot x. So I'm not going to type, I will select and say that the mean in our problem is 36 minutes. And once again, instead of going in the same row, I'll put a comma and hit enter so that it doesn't become a very long line. And then we need to provide what was the sigma that was given. So as I start typing, so sigma dot x, select that. Sigma was 6 minutes, comma, hit enter, sample size, so n dot x. So n dot x, 28 restaurants. And the final thing we need to provide is confidence that we are interested in. Confidence level 0.9. So when you run that, it will give you a lot of information, but also gives you 90% confidence interval. So the function I used started by using a library that we are going to use going forward. And then the function is z.sum.test, where we provide mean of x, we provide sigma, we provide sample size, and confidence level, 0.9. So this is what we use in R to get a solution. So here we are plugging in the values, doing the calculations, but here you can get the confidence interval directly. And this will become like easier and easier, and it will save a lot of time as we go forward with more complex calculations. So this kind of function will save a lot of time for us. So 90% confidence interval for mu that we got was 34.13 minutes and 37.87 minutes. Now there is another part of try it which is asking for 95% confidence interval for mu. So once you have this formula, the only thing you have to change is change this 0.9 to 0.95, and that will give you 95% confidence interval.